Okay, welcome back. 4.3, increasing, decreasing functions and the first derivative test. Okay, so we'll see the mean value theorem here and kind of the proof of one of our theorems. First off, let's just define decreasing and increasing. So some definitions. First off, increasing. That means when x1 is to the left of x2, then f of x1 will be less than f of x2. Okay. Secondly, for decreasing, supposing x1 is again less than x2, then f of x1 will be greater than f of x2. So you try to make an algebraic definition here as opposed to our sort of graphical way of thinking. We want to get away from sort of visual methods because sometimes, if you're working in, I don't know, different fields like quantum physics or something, the intrinsic idea of increasing and decreasing may not be there. So you have to have other methods for dealing with the issues, I suppose. I don't know how true that is. I've never studied the field. But I can imagine that maybe you would have to have a different criteria for increasing and decreasing in other sort of math universes. Okay. So anyways, let's look at theorem 4.5. I'll shut up. So here, criteria will look familiar. They'll look like the familiar criteria for the mean value theorem in particular. And so we want to be given a function f that's continuous on a closed interval and differentiable on an open interval. Given a function f continuous on the closed interval and differentiable on the open interval, we have these kind of statements. Okay, we could look at the derivative and tell if the function is increasing or decreasing. So first off, if f prime of x is greater than 0 on an interval from a to b, that implies f of x is increasing on this closed interval from a to b. If f prime of x then is less than 0 on this open interval from a to b, then f of x will be decreasing on the closed interval from a to b. Finally then, if f prime of x is equal to 0 on a to b, then f of x is constant on a to b. Okay, so we know this to be true just intuitively from the pictures. If you have a graph such that its derivative is negative, what does that mean graphically? Well, that means in a particular interval, for example, here to about right here, all of the values of the slopes of the tangent lines will be negative. Okay, so you'll have little tick marks going down, and it kind of implies that the function is decreasing. Okay, so at least pictorial-wise, and you're not always going to have pictures to rely on, but at least I guess we do here. So the idea, why do we need to make these kinds of definitions is because eventually you won't have pictures to deal with. If you're in 10 dimensions, how are you going to deal with that? So anyways, that's kind of what I was getting to when I was complaining, we need a different definition for increasing and decreasing in different contexts. Okay, which probably isn't true. It seems like increasing and decreasing is kind of a solid, a solid thing. Okay, so anyways, again, I'll shut up. So for theorem 4.5, if the derivative is positive, it's increasing. If the derivative is negative, it's decreasing. If the derivative is 0, it's constant. And we can use the mean value theorem to prove this material. So first, proof, let's just look at this first line. We're supposing all of this material. So suppose f is continuous on a to b, differentiable, I'll just write diffy, on the open interval from a to b, and f prime of x is greater than 0 on a to b. In that case, from the mean value theorem, from the, we'll just abbreviate MVT, from the mean value theorem, there exists a C in this interval from A to B, such that if we take two particular points in this interval, so it'll hold for any 2 points in this interval, and we'll just consider generic x1, x2. There will exist a C such that f prime of C will equal f of x2 minus f of x1 all over x2 minus x1, where I just did not note that x1, x2 are in the interval AB. Okay, so supposing that x1 is to the left of x2, in other words, x1 is less than x2, we could say the following inequality, x2 minus x1 will be greater than 0. Okay? We are already saying that, or we have supposed that f prime of x will be greater than 0. So we're saying that f prime of c, in fact, will be greater than 0. And so for this to hold, this inequality to hold, if this is greater than 0 and the derivative is said to be greater than 0, it forces the numerator to be greater than 0. So hence, it must be the case that f of x2 minus f of x1 is greater than 0, right? Because the derivative for any x in this interval is greater than 0. So this derivative in particular has to be greater than 0. So we know that x2 minus x1 again is greater than 0. That forces positive over, we need positive over positive. So this thing has to be greater than 0. And then we could solve this inequality so that f of x2 will be greater than f of x1 in this interval, which then just goes to show that we have an increasing function. Okay? So by definition then, if the second guy is greater than the first guy, it's increasing. And that's what we have. The second guy is great. It's just written in reverse here. Okay, hence f of x2 is greater than f of x1 for arbitrary x2, x1 in the interval. And so the conclusion that f of x is increasing follows. Okay, so it's an application of the mean value theorem. I think intuitively, though, it's pretty clear. It's just we need these higher power methods in case we don't have the geometry flying around. You know, people didn't have graphing calculators back in the day, so we had to figure out other methods. And sometimes your graphing calculators will lie. Okay, so there are issues with the calculators. At least there used to be. You know, they probably ironed most of those out. Anyways, let's try an example. We'll do an easy one. Example 1 in the book. Let's find it and go at it. All right. So where are you? Example 1. find the open intervals on which this function is increasing or decreasing. So example 1, the function given to us is a simple polynomial. I won't, in general, ever really check for continuity and differentiability like I would in the previous chapter when I was trying to see if Rolle's theorem applied or if the mean value theorem applied. Anyways, how is this going to work for us in practice? Well, you'll find the derivative. You'll say, okay, f prime of x is 3x squared minus 3 halves times 2x. Okay, let's clean that up. It's 3x squared minus 3x. You'll find the critical numbers. Okay, so find the places where it's equal to 0, the places where it's undefined. Okay, this guy's defined everywhere. All I have to do is find where it's equal to 0. Okay, so let's factor out 3x. I get x minus 1 is 0. Set each factor equal to 0, so I get x is 0 and also x is 1. So what I like to do is a number line. The book will do a chart, okay, but I'm just going to do a number line. You'll do a test value. You'll do the sign of the test value and then a conclusion. And on the number line, you're going to label the critical numbers. Okay, only the critical numbers. Do not put like here's 0 and here's no. Just label the critical numbers. Okay, and because later on we have to work with higher derivatives in this process, you might want to label this number line as the derivative number line. Okay, okay, so f prime of x, we have a critical number at 0 and a critical number at 1. Okay, we want to find the intervals on which it's increasing and decreasing, and in particular then there's 3 intervals. So I pick a test value from each interval. So here, maybe use a different color, right? So I'll pick x equals -1, and we're plugging these values into our derivative. Okay, so if I plug -1 into here, and I'll use this form because all I'm looking for is the sign. 3 times -1 is negative. -1 minus 1 is negative. Negative times negative is positive. And so our conclusion is that it's increasing. Okay? From 0 to 1, I'll pick x is 1/2. Plug that into my derivative formula. So 3 times 1/2 is positive. 1/2 minus 1 is negative. Positive times negative is negative, so it's decreasing. And then finally, another test value. You pick anything you want, as long as it's not equal to 1 or 0. So you cannot pick those values. That's where the derivative will be equal to 0. Okay. So anyways, x is 5, so 5 times 3 is positive. 5 minus 1 is positive, so it'll be positive, and on that interval it's increasing. Okay. So that's the idea. The book will make them more and more complicated. From here, though, we can parlay this into an analysis that leads to the maxes and mins. So we know that maxes, relative max and mins are critical values, and we can tell whether or not it's a max or a min by this kind of analysis. Okay, in particular, the function's going up and then it's going down. So you expect a hill right here, and then we would conclude this is a maximum. Right here is kind of a valley on the graph, so we would expect this to be a minimum. Okay? And that turns out to be the case. So it's called the first derivative test that allows us to make these conclusions. Section 2, the first derivative test. Okay. So this is then Theorem 4.6. I'm not going to prove this. It may be proven. It is proven in the book. So I'll leave that to your reading. Okay, so please go in there and take a look at it. But here's the sort of lowdown. If you're doing your graphical analysis, you plotted your critical number, and it goes from negative to positive. That means you're going to have a hill, a valley scenario. So the graph is going down and then it's going up. So it's going to be a min value at C. Okay, so this tells me it's a relative min at the point c comma f of c. So the min occurs at x equals c, and what is the min? The min is f of c. Okay? Secondly, then, if it's the other scenario, so you're finding the sign of the derivative is first positive and then becomes negative, that tells me there's a relative max at this point, c comma f of c. And then thirdly, if the sign of the derivative does not change, in other words, maybe it goes from negative to negative, or on the other hand, it goes from positive to positive, there's really no max or min at this particular juncture, right? So we'd say no relative max or relative min at the point c comma f of c. Okay, so let's look at a couple more here. And this time we're going to be doing the chart analysis, and then at the end making a conclusion about the maxes and mins based off the first derivative test. Okay. So let's look at 21. And they give us a parabola, f of x equals x squared minus 4x. So we expect it to have a minimum value at the vertex. Okay, so it's minimum because the leading coefficient on x squared is it's positive, right? So it's a happy face parabola, and it'll have a min value. Okay, let's do the calculus though. So the derivative is 2x minus 4. I need the critical numbers, so I'll set that equal to 0. And then I'll plot my critical numbers on my sign chart for the derivative. So x equals 2. I just write 2 there. See, I'm not plotting 0 or anything, just plotting the critical numbers. Then I need test values, signs, and conclusions. All right, so try x is 0. I'm plugging it into my derivative. 0 minus 4 is negative, so it's going down. And then x equals 3. 6 minus 4 is positive, so it's going up. Okay, so it's going down and then up. It's like a valley, right? So there's going to be a min value there, and we'll write relative min at the point 2 comma f of 2. Okay. So it's basically the vertex. If you plug 2 back into our function, then it's 2 comma 4 minus 8 is negative 4. Let's look at 25. So this time they give us a cubic function. F of x is 2x cubed plus 3x squared minus 12x. Its derivative, f prime of x, is 6x squared plus 6x minus 12. Set it equal to 0. So 0, I'm going to factor a little. 6 times x squared plus x minus 2. You can divide both sides by 6, and you're just left with x squared plus x minus 2. Now, factoring that, it'll be x, it has to be plus minus. The bigger number has to be positive, and the smaller one negative. So I have 2 critical numbers, negative 2, and then x equals 1. So I go over to my number line for the derivative. Here's my f prime of x. Plot negative 2, plot 1. I only plot the critical numbers. And then I need my test value, my signs, conclusions. Okay, so test value, I'll try negative 3. And I'm going to plug it into here. So long as I didn't change the sign of the original function, you can use this factored form. Okay. Sometimes if you multiply both sides by a negative, it'll change this, and you can't do that. But as it sits, I've kind of preserved the sign of the original derivative, so I'm not going to have to worry about going back to here and then doing some heavy-duty arithmetic, right? just go to here and plug it in. Okay, so -3 plus 2 is negative. -3 minus 1 is negative. So negative times negative is positive, and so it's increasing. Okay, so I'll try x is 0. Plug in 0. Positive times negative is negative, so it's decreasing. And then try x is 3. Positive, 3 plus 2 is positive. 3 minus 1 is positive. Positive times positive is positive. So it's increasing again. Okay, so it's increasing and then decreasing. That means there's a hill, so there'll be a maximum. And then it's decreasing and increasing. That'll be a valley, so it'll be a minimum. Okay, so there's a relative max at the point -2 comma f of -2. So if I plug in -2 into this, I will get -2 comma 20. And then there's going to be a relative min at this other point, right, where it goes down and then up. So relative min at the point 1 comma -7. So the x value is 1, and then plug 1 into the function. 2 plus 3 minus 12 is 5 minus 12, which is the -7. So that's how I'm taking these values now, I'm plugging them in here to get the actual point on the graph. Okay, let's look at just 2 more examples, and we'll call it quits. So this is example 3 from the book. And we have f of x equals x squared minus 4 to the 2/3. Okay, the domain of this thing is all real numbers, but I think when we get its derivative, there's going to be some issues, right? So let's look at the derivative. F prime of x is 2/3 times x squared minus 4 to the 2/3 minus 3/3 power, or minus 1/3 power, times the derivative of the innards, which should be 2x. Okay. Clean that up a bit, and you get 4x all over 3 times the cube root of x squared minus 4. Okay, so this guy has some places where it's not, where the derivative is not defined. We haven't really seen that in my examples to this point. So anyways, what you're doing is basically setting the derivative equal to 0, which will come down to setting the numerator equal to 0. Right? So setting the numerator equal to 0, you get one of the critical numbers is just 0. Setting the denominator equal to 0 to find where the derivative is undefined. I can cube both sides. Okay, so I get 27 times x squared minus 4 is 0. Divide both sides by 27. X squared minus 4 is 0. Add 4 to both sides. X squared is 4. Square root properties then says x is plus or minus 2. So the derivative is not defined at these 2 points. And if you remember, our critical numbers are places where the derivative is equal to 0 or the derivative is not defined. So we actually have 3 critical numbers. Okay, so let's go and plot those. I have one at -2, one at 0, one at +2, and this is the sign chart for the derivative. I need to do test values, I need to do the signs, and then I need the conclusions. Okay, so let's try x is -3, x is -1, x is 1, and then x is 3. I'm plopping everything into this guy right here. So if I plug -3 into here, well, the denominator is going to be positive, right? So -3 squared is 9. 9 minus 4 is a positive number times another positive number is positive. So the sign for the first guy is going to be in the denominator, it's going to be positive. In the numerator, so in the denominator it's positive. In the numerator, it's 4 times -3, which is negative. Right? So I have a negative over a positive, which is negative. In other words, this thing's going down. Let's try -1. In the denominator, I have -1 squared is +1, minus 4 is negative. Okay, so I'll have a positive times a negative is negative in the denominator. And then the numerator, if I plug in -1, I also get another negative. Okay, so it's going to be a negative over a negative, which is equal to positive. In other words, it's increasing. So let's go on to x equals 1. If I plug that in the numerator, it's positive. And the denominator, if I plug in 1, it's a negative times a positive is negative. So it's negative and it's going down. Lastly, when I plug in 3, I'll have a positive over a positive. So that's positive. In other words, it's going back up. So in this case, I'll have a min here, and then a max here, and then another min right here. Okay, so let me write that out. There's relative mins at -2 comma f of -2. So I have to plug -2 into here. Okay, and that's going to give me 0. And also at 2, there's another min. Plugging 2 into there, 4 minus 4 is 0, so that's also 0. And then there's a relative max in the middle here. And that's at 0, comma, -4 to the 2/3, whatever the heck that is, right? So it would be -4 to the 2/3. To evaluate that, -4 is 16, and then I just need the cube root of that. So this is 0, comma, the cube root of 16, whatever that is. Okay? Okay, let's look at one more. So this is 45 in the book. I have f of x equals 3 minus x times e to the x minus 3. Okay, so I need the derivative f prime of x. We could rewrite this. Let's distribute 3e to the x minus 3 minus xe to the x minus 3, and then take its derivative. So the derivative of the first part will just give you back 3e to the x minus 3, and then the derivative of x minus 3 is just 1, so the chain rule wouldn't really give us anything. For the next part, I need to do a product rule, so I'll leave x alone. I'll have x, and then the derivative e to the x minus 3 we just found was e to the x minus 3. And then plus the derivative of x is 1 times e to the x minus 3. Simplifying a little bit, at the end of the day, I'll have 3 of these minus 1 of these, so 2e to the x minus 3. And then minus xe to the x minus 3. Set that character equal to 0. Factor it. So 0 equals e to the x minus 3 times 2 minus x. Exponentials will never equal 0. So, I mean, you're setting each part equal to 0 to solve for the zeros. This part won't give you any information. E to any power is not equal to 0. So I go to this guy, x equals 2 is my only critical number. Go to your number line for the derivative. And then do your test values, your signs, and your conclusions. So I'll try x is 0 and x is 3. So when I plug 0 into this expression, I'll have e to any power is positive, right? So it can always kind of just not even consider that. 2 minus 0 is positive, so it's positive, it's increasing. When I plug in 3, it'll be 2 minus 3 is negative. So it's negative, it's decreasing. In other words, it's going up and then back down. So there's going to be a hill there, and there's got to be a max on the top of that hill. So a relative max at x equals 2 of whatever that is, right? Of y equaling 3 minus 2 is 1. So e to the 2 minus 3 is negative 1. So as a coordinate, 2 comma e to the negative 1, if you would rather. Okay, so that'll be good enough for now. Thanks for watching.